Okay, so as many of you have been asking me, we do have a test on Thursday. I thank you for reminding me because I had been planning as if the exam was next Thursday, but it is this Thursday. So we're going to have the last day that's going to have material on the exam is going to be today. On Wednesday, we're going to review. Tomorrow's recitation is going to be more of this material that we're doing today. So the last piece of material that's going to be on the exam is going to be the flux. So just to quickly go over what's going to be on the exam, force between charges and distributions of charges, calculating the electric field for point charges and distributions of charges, calculating the electric potential from distributions of charges. Really, all of those are really the same. They're just slightly different equations, but the way that you apply them is almost identical. Given some electric field, finding the force on a particle, so that's F is equal to Q times E, and then how to go between the electric field and the electric potential. So that was what we did last week. So any general questions about the exam? And you did want to talk about it, or you had some questions? There's just that.
Yeah.
Okay.
Yeah.
Sure.
Are we going to get formulas, or we have to memorize everything?
There'll be some formulas. I guess that's not specific, and probably not the answer that you're looking for. The way that I try to format my exams is such that there's very little that you need to memorize, but you really do need to understand how to apply the formulas. And I think perhaps even more so than you might have last semester, because last semester you might have had more formulas. You see, like, even with the things that we've done so far, there really aren't that many formulas. It's really more understanding what the pieces of them are and how that applies to different situations. So looking at the old exams on the repository of exams, that's probably going to be pretty representative of the type of equation sheets that you're going to get. And I might add a little bit more than that, but don't expect me to write down what DL is for everything. I'm not going to give you what DQ is. You need to know that DQ is lambda DL, know what lambda is, what DL is for different situations. But I'll give you Coulomb's law. I'll give you the relationship between force and electric field. I'm not sure if I'm going to tell you how to do this with distributions of charges. You have this, but you should understand that when I'm trying to do this with a distribution of charge, or when I want to find some electric field or electric potential, that's really to say that dE is equal to 1 over 4 pi epsilon naught dq over r squared r hat, and dV is equal to 1 over 4 pi epsilon naught dq over r. I really want you to understand, without me prompting you on the exam, how these are related to this and this. So I'll probably give you these. I'll think about whether or not I'll give you these, but I think it's fairly natural. I will give you this. I will give you grad of V, negative grad V is equal to E, and V is equal to the negative integral of E dot dl. I'll give you those two. I'll give you these two. But everything that comes out of these 4 equations are things that I want you to understand how to arrive at yourself. And so, yeah, you can just write this down, but you should also understand that this comes from relating this to this. Okay. And really, if I think about it, that's about everything that I would possibly give you, aside from telling you that, like, dq is equal to lambda dl, and then tell you what all the dl's are. I'll give you what the gradient is in Cartesian coordinates and polar coordinates, and I'll give you what dl is in Cartesian and polar coordinates. Not the dl vector, not the dl without a vector. So really, it's going to be all of this plus what the gradient and infinitesimal length vector are. We'll be thinking. things that I'll give you. Okay. Other questions concerning the exam? Okay, so let's go ahead and move into solving the homework. So this one
is going to be on the thing too. You're going to give us the equations for flux.
What's that?
Since flux is going to be on there, you're going to.
Yeah, I'll give you Gauss's law too. I'll give you Gauss's law. Forgot about that one. So, and this leads into what we're talking about today. So I'll give you that one too. Okay, so let me erase this in this space. All right, so starting today is new material that we haven't talked about in class. So I did want you to kind of work on it and struggle on it to some extent. So you came in knowing some of the pitfalls of the types of calculations that we're going to be doing today and tomorrow in recitation. And these are related to flux. And so the way that electric flux is defined for some flat area is to say that the electric flux, which is represented by some capital Phi sub E, is equal to the integral of E dot dA vector. Okay, so you'll see this dA vector and this ds vector, and there are some differences between them that I'll talk about in a second. But for now, let's just talk about the flux through some flat area. And so this is to say, if I have some flat area like this that's oriented like this, so this is kind of like a page that's like this. The way that you calculate flux is you sum up all of the electric field that goes through all of these little infinitesimal areas. So there's some dA vector associated with the total area, and were this to be some closed surface, the way that this dA vector is defined is going to be such that it points out of the closed surface. So there are several important pieces to this. First, we have a dot product, right? Same way that when we were looking at defining the electric potential and saying that the electric potential is equal to the negative integral of E dot dl. It was very important in that case that if we had some dl that parameterized some infinitesimal path, that we're adding up all the electric field that was in the same direction as the path. And we're doing the same thing here. So to give you some intuition in how this works, if I have some electric field that points like this, what should my flux be here? 0. Why?
Parallel to the...
Exactly, because this is parallel to the surface. So the way that you think about flux is I want to add up all the things that go through the surface. So if the electric field is moving in this direction and the dA vector points this way, then the flux is going to be 0. We could look at the maximum case here now, where E is in the same direction as dA. And so here, when I take this dot product, this is just going to be E times dA, not vector E dot dA. This reduces just the product of the magnitudes of these because the angle between them is 0. Okay. So this is how you would talk about flux through a single area. But when we talk about Gauss's law, what we're really doing is we're trying to find what the total flux is through some closed surface. And what Gauss's law says is that the flux through the entire closed surface is going to be equal to the charge that's contained within the surface. And you can think about this, and it makes sense on an intuitive level, that if I have some charge of plus Q here, this is going to radiate outwards like this. And if I enclose this with some surface, we'll just choose a sphere because that's actually the best way to do this one, and I add up all of the flux leaving the surface, that's going to tell me something about what the charge is inside it. So if I have some surface that I define there's no charge on the inside, there's not going to be any flux leaving it. If I have some plus Q here, there's going to be some amount of flux leaving it. But if this is larger, the flux is going to be larger. And so we can see that by adding up all of the little pieces of electric field that are leaving the surface, we can say something about the total charge that's inside it. Now, this is going to get to the difference between this and this, and this, and this. So when I define dA vector, I'm talking about only one surface. When I talk about ds, for the case of a sphere, it is one surface, but ds has to do with the total surface that bounds some object, and that's really what this circle here means. This means over the closed surface. Okay, so this leads us into the calculation that I had you do for class today, and that was to find what the charge was inside some cube given some electric field. So in order to do this, when we say this is the positive x-axis, this is the positive y-axis, and the positive z-axis, and this is some cube that has sides of A. Okay? Now the electric field that I gave you said that E vector is going to be equal to E0 xy divided by a squared times y hat. And so what we need to do in order to find what the total charge is contained in this cube is to find what the flux is out of all of the surfaces and then add them up. That's really what this integral over the closed surface means. So the integral over the closed surface is equal to the sum of the integrals over the areas. So this is E dot ds, and this is E dot dA, and I'll give this an index, the sum over all surfaces. So this is from I is equal to 1 to I is equal to 6 in this case, right? Because there's 6 surfaces here. So we need to find the flux out of the top, the bottom, the left, the right, the front, the back, and the front here. And so the first thing that I had you do is I wanted you to define what dA was for each side of this cube. So I actually gave you a table in the notes that define this, and that I also said on the test, be very careful. That's not something that you want to memorize. It's something that you should understand how to come to the conclusion of what each dA is, because that could change if I invert one of these axes. So you have to be a little bit careful here. So let's make this table for dA. So this is what dA is, and then this is which surface it is. So for the front, what should my dA be? Well, dA's got two parts. It's got the product of two infinitesimals, and it also has some unit vector. And the unit vector, by definition, always points out of the surface. So for this front surface, what's the unit vector that points out of it? X hat, right? So this is going to be some x hat. And then what are the infinitesimals that make up all of these little boxes here?
dy dz.
dy dz. Good. Do we see that? Because if I rotate this so that it's flat in the yz plane, this is really what I'm looking at here. This is z, this is y. And then this little box has a little bit of dz and a little bit of dy. Okay. And it also points in the x direction. And so we can go through this whole process to find what all of these are. I'm missing top and bottom. Top, bottom. So for the back, this is going to be minus x hat dy dz. Why am I saying it's minus x hat? Somebody from over here. What do you guys think? Yeah.
Because it's going the
Exactly.
opposite way.
Exactly. So the front, the vector that points out goes this way. For the back, the vector that points out is this way, which is a minus x hat. Good. So now when we look at the left, this is going to be a minus y hat dx dz. For the right, this is going to be a plus y hat dx dz. For the top, this is going to be a plus z hat dx dy. And I need a new piece of chalk. And for the bottom, this is going to be a minus z hat dx dy. Okay. So now that we have all of these dAs determined for every face of this cube, we're ready to calculate what the flux is out of it. And if we look at this, we see something really convenient here, and that has to do with the way that this E is defined. what's the direction that E is always going to point? In the y direction, right? So any one of these dAs that is not in the y direction, when I take the dot product, it's going to be 0, right? Because the electric field always points this way. So if I look at this surface, these are going to be perpendicular to each other. Same thing with the back, same thing with the bottom, same thing with this one right here, the front. Okay. So when I take these dot products to find the sum out of the total surface, really the only ones that I'm interested in are the left and the right. Okay. So let's go ahead and take those dot products and put those together. So this is going to say that this is going to be the integral of E0 x, y, and in principle this is a double integral because we have a dx dz. Y hat dot minus y hat d, this is dx dz. Dx dz, okay, plus the integral of E0 x, y, y hat dot y hat dx dz. So we have, this is the left and this is the right. You can see with the negative sign and the positive sign. When we take these dot products, this one's just going to be, give me a negative sign out front. This one's going to be, give me just positive 1. And now we see something kind of weird here because when we look at these integrals, we have the integral of minus E0 xy dx dz plus the integral of E0 xy dx dz. So our variables of integration are x and z, but we have this y here. Yeah?
Where'd your a squared go?
I absorbed it into the
Okay.
into the yeah, I should have one over a squared here. Yeah. Okay. I heard some murmuring other places. Was that the concern? Yeah. Yeah. So I just dropped it. It's a constant. So when we're looking at this and we see we have this y here, that should prompt us to think that there might be something that we need to worry about because we're integrating with respect to x and z. So we need to figure out how we can evaluate this y for each one of these cases. Now, if it turned out that y was some function of x or z, we would just plug that in and evaluate the integral. But that's actually not the case here. So what we need to consider is we have this electric field, and it has different values for different y's. So when we're looking at these faces, we have this face over here and this face over here. What is the value of y for this face? 0. Why? It is parallel to this one. More specific. Why is this face y is equal to 0?
It's on the xz plane.
Yeah, it's on the xz plane, and for every value on this surface, the value of y is 0, right? How about this one? It's going to be a, right? Because for every value on the surface, for every position on the surface, the value of y is a. So when we're looking at this integral, what that means is we need to evaluate this one for y is equal to 0, which actually makes this whole integral 0, and this one for y is equal to a. Okay? So when we do that, then we're going to need to integrate this over the boundaries in x and z. X is going to range from what to what? Where does x start and where does x end?
0 to a.
It goes from 0 to a. So this is x is equal to 0 to x is equal to a. How about z? Yep, same thing. Z is equal to 0 to z is equal to a. So when we do this integral, what we end up having, I'm going to cancel one of these a's with this a I got from the y here. We have some E0. Integral of x with respect to x is going to be x squared evaluated, x squared divided by 2 evaluated a gives me an a squared over 2. And then the integral of z is going to give me, this is just going to be a, right? Because the integral of dz is just going to be z evaluated from 0 to a is a. So then that cancels this, and then our final answer is, let me move this up here. So this is going to be the total flux. This is going to be E0 a squared over 2, which is equal to q in divided by epsilon naught. And to find q in, we just multiply both sides by epsilon naught. And that's it. Okay. So the game that we're playing here is always going to be the same. It's just going to be slightly different depending on what the electric field is that I give you, right? So you're going to need to be able to define what dA is for every one of the faces of the cube, and then evaluate what the flux is through each one of those faces. This one happened to be pretty straightforward because several of the dot products were 0, and then this face, the flux through it was 0 because the value of the electric field was 0 there. Okay. Any questions about this? Yeah.
Why does the E sub naught term stay, but we don't have the 4 pi for some of the other terms? Well, I guess I see why we don't have the R, but why don't we have the 4 pi?
Well, this just comes from the definition of Gauss's law. So I found what the total flux out of this surface is. Now, where you might find a 4 pi is if the surface that I used here was not the cube. If I did a sphere that went around, and that would be hard to do with this particular electric field. But say for instance, I wanted to find what the electric field was produced by this charge. Because I know the electric field is spherically symmetric, it's natural to choose a sphere for my Gaussian surface so that the dot product is going to be, the angle between them is 0. So this would reduce to the integral of E times ds, no vectors. E is isotropic, it's the same magnitude in all directions. So I can pull this outside of the integral because it doesn't vary over the same variables as ds. So this is going to be E integral ds. Now this is just the surface area. And for the sphere, that's where you're going to get a 4 pi r squared. Okay. But it really comes down to what surface you're using. And because this was a sphere, we ended up getting these like a squareds that are popping out of that integral of E dot dA. Yeah.
Because I'm the cube.
Yeah, because it's cube. Yeah. Other questions?